Okay, so I guess I'll do 10 minutes just to kind of go through the solutions, and I won't go into all the details of the solutions, so you guys can still work through all that part. And I'll stick around until, you know, as long as you guys want to stick around. Well, I mean, I have to go get my kid at some point, but yeah, I'll stick around after I go through this. But I thought before, you know, if anyone wants to leave, they can at least see this part of it. So all right, so there are the different parts of the case study exercise, and so we can kind of click through this. And so summary statistics, there's the table will get you those distributions, right? And so you can see the distributions of HPV status and of gender, and then here's the association between gender and HPV status. This is the cross tabulation, and then chi-square test will pull up a chi-square test for association. The p-value is quite strong there. And if you look at it, so these are column proportions here, and much more of the male, the HPV positives, a much greater percentage of males are HPV positive rather than HPV negative compared to females. Okay, and so, yeah. It might actually be better if you put margin equals 1, then it'll give you proportion across the rows, which is a little easier to understand. So you might try that little twist to this one little part, put margin equals 1, and then it'll tell you within females and males separately what percent are HPV negative versus positive. Okay. And then some other tables, which I won't go too much into, about stage of disease and M stage, N stage, and T stage, which they've broken it out into substages here too. So if you want to mess with it, you might have to collapse it. All right. And then some survival status. And so the first thing we'll look at is survival status by HPV status. The log rank test is here. That's nearly significant. P-value is 0.07. We see what we expect to see, which is that the positives have a better overall survival than the negatives. The hazard ratio for positive relative to negative, it's about 0.77, okay? So 33%, reduction in hazard of mortality for HPV positive patients versus negative patients. All right. Then here it is by gender. Gender was also significant, where males had better survival than females. And I thought that maybe this was because of the association between gender and HPV status. And so I did a Cox regression where I controlled for HPV status over here. But in fact, that didn't really change too much. It changed a little bit, the significance of gender in the model, but it didn't wipe it out. So it's more than just HPV status that's reflecting in that difference in survival between by gender. Okay. And then here's stage of disease, and this is just making that new variable. And then there the p-value is quite significant. And we see that stage 4 does do quite a bit worse than stage 1, 2, or 3, which is what you'd expect, and we do see a kind of ordering here, although stage 2 and 3 are kind of lumped together there in terms of those Kaplan-Meier curves. But stage 4 is clearly has a reduced survival relative to the other stages. Okay, so here's the RNA-seq. So we start out by doing some log transformation. And then this is a multidimensional scaling plot, which, I've color-coded HPV positive and negative. If you just take all the genes, of course, everything looks kind of intermingled, although there are some HPV positives that are separate out over here a little bit. But that's, if you look at it on a global scale, sometimes what this plot is useful for is in experimental design. You want to see kind of clusterings of your design factors, especially if you're using something like a mouse model and you're doing something drastic like knocking out a gene or something like that, then you'll see big differences or diets or something like that. In this case, since this is, observational data, then we don't expect to see any huge separation here on this scale. But what we're going to do then is redo this thing once we've kind of restricted to genes that are different between HPV positive and negative, and then relook at that same plot. All right, now this is the box plots of on the raw count data, and you can see that you can't really tell much from these things, not very helpful, because all these, the scale here is dominated by the highly expressed genes. So you can't even see the box. But if you take log 2 transformation, that works pretty well. And then you can see what the distributions look like for each sample as you're looking across the samples. This is, within each sample, this is all the expression of all the genes. And we see some differences, some shifts in the median and whatnot. And so the normalization kind of corrects for this. And kind of, in essence, you can see the effect of the normalization by looking at the box plots after normalization, and the box plots look much more aligned with each other after that. So we'll check that a little bit later. Do some filtering. We filter out everything with a mean count less than 10. So that's a little bit arbitrary, but the idea is if it's that lowly expressed and we don't really care about it, and so that eliminates almost 4,000 genes. And then this is the TMM normalization, and so there's this calc norm factors function within the edgeR package. And if you do method equals TMM, that's that TMM normalization, and it creates this, DGE is digital gene expression, by the way. That's what that is short for. It's another one of those 3-letter things. But although this is just something we made up, we could call this whatever we wanted to, right? And then that's, all right, so we'll keep on going. This is a differential expression with lemma. And so in order to do that, we have to create a design matrix. And so you have to run this model matrix command initially with HPV status. And then if you want to adjust for batch number, you can throw that in there too. And I don't know if they talked about this, but the 0 here basically means that to not include the intercept in the model, which to me actually makes it much easier to use lemma when you exclude the intercept. So if you put the 0 in there, it takes it out. And then what you have to do then is make a contrast matrix. So you have to, for instance, if I want to test between negative and positive, and so this is what the design looks like here, then I have to say use this make contrast command and say, I want to test for this one minus this one. And so that's exactly what goes into here. And the levels equal design just tells the function to look in this design object that I created up here to get those things, okay? And so that's going to be what I'm testing. And it is important to know the difference, negative minus positive, because then you know how to interpret the fold change. So a negative fold change, right, it's going to mean positive, excuse me, the log fold change. So a negative log fold change, right, or a negative difference on the log scale, right, then means that the positive has a higher expression than the negative. And vice versa, if you see a positive difference, then clearly the negative is more highly expressed than the positive. This is important to keep in mind. Sometimes people get that mixed up, and you don't want to do that. Let's see. So this is this VOOM transformation. And so this is calculating this mean variance trend plot. And so what we're trying to do is look at how the variance changes with the mean. And if you look at this kind of plot on the raw count scale, you'll see that the variance actually increases with the mean, okay? That's to be expected. That's called over-dispersion. And so what you see is as the counts get higher, the variability gets bigger, okay? And once we do this log 2 counts per million transformation, it's kind of overcorrecting for that. And so now what we see is that we actually have higher variability in the lower counts, okay? And so that's why this trend looks like this. Normally, on the count scale, you actually see the opposite effect, okay? But after we do the log transformation, it overcorrects and it looks like this. Okay, so the idea here, of course, is that we have, these are the variances, and with lemma, the idea is, well, let's try to pool these variances toward a common estimate, which is reflected by this red trend line, all right? And actually, Voom calculates these weights, which I'm not going to go into, but and that's how it adjusts for that. That's how it models this relationship between the mean and the variance. Okay, so then we go into this bit over here. Let's see, this is just elements of what's returned. So the return object from Voom we're just calling V because we're lazy, we don't want to type much else. So we just type a V. And so we've got this is the matrix of expression values on the log2 scale, the log2 CPM, counts per million scale. And then we got the weights thing here, which you don't have to worry about what's in the weights, just know that it's being used. And then we have this design matrix here, which is the original design matrix that we used. Okay, and these are the scaling factors. So this is what we use to rescale the data. And then when we look at the transformed data, it looks like this. And you can see, obviously, the box plots now are much more aligned, at least the median and the upper kind of 75th percentile. You still see differences along the 25th percentile, but the idea is to try and line up the overall global average expression across the samples so that that's not really changing. And the whole idea behind this is that, well, it doesn't seem biologically reasonable that we would see wholesale shifts in gene expression from one sample to the next. Rather, we think that it's just certain genes that are changing. Okay, so that's the kind of biological support for doing that normalization. Okay. All right. So lemma here, we run, so the standard thing to run lemma, and this takes a little while when you're first running it, so I hope you guys do go back and try and reproduce this on your own by going through the things. This lmfit, eBayes, and top table, okay, are the kind of three functions that you want to run. This fits a linear model. This thing you use, and it tests for the actual difference between, in this case, HPV positive and negative, because this contrast matrix contains the test that we want, which is, hey, test for the difference between positive and negative. So the eBayes returns that estimate of that difference, and then top table just puts it in, which I didn't print out top table here, but I think you guys ran it in the other session. Top table produces like a tabulated list of your results, right? Where you first, each row is a gene, and then it gives like the difference in expression and a p-value and a couple of other things too. But the main things are the difference in the expression and the p-value. Okay, and so then we can kind of try to look at how many genes we want to look at, depends on what kind of adjusted p-value we're comfortable with. There's a lot of differences because we have a very large sample size, so we have a lot of power. So we have a lot of things that are different. Even at an adjusted p-value of 0.05, we still get 7,000 genes, which is about a third. Actually, it might be more than a third. Okay, more than a third of the genes. So there's a lot of genes, okay? So we might want to look at a more, even if you look at a p-value as small as 10 to the minus 10, you still get almost 1,000 things, okay? And then you can incorporate a fold change threshold, and the top table gives you a column called log fold change, which is just a difference. And so we can compare that to log of 2, and then that would check out whether or not the fold change is bigger than 2, okay? And so that incorporates, so here we can check all these genes that pass these different thresholds of both p-value, the p-values from 10 to the minus 2 to the 10 to the minus 10, and this is p-value threshold coupled with fold change threshold, all right? And then the so-called aptly named volcano plot, right, which gives you a plot of your results. Each dot in there is a gene, right? And then on the x-axis, you have log fold change. So the further out over here, the more biological significance you have, bigger difference, right, in expression. And then what we've done is transform the p-value by taking minus log base 10, all right? And you get, so a value of 10 here means that this p-value is 10 to the minus 10, okay? Which is very, very small. A value of 3 here would be a p-value of 10 to the minus 3 or 0.001, right? So we've transformed it to make it easier to visualize what the p-values look like in a plot, because you can't really look at a plot of 10 to the minus 10, it'd be hard to visualize. And so a bigger value here corresponds to a smaller p-value, so the further up you go, the higher in terms of statistical significance you are. And so the idea here is that we can make a cut, make some kind of threshold on the x-axis scale that corresponds to biological significance. And I forget what I put here. I think I put a threshold of a fold change of 2, okay? Which corresponds on a log 2 scale of plus and minus 1. And then the p-value threshold, I think, is 10 to the minus 3. And so that's what this 3 here is. So that's a value of 3. So anything in these 2 quadrants is passing our filter, okay? And we color it red so it looks like a volcano. All right, so now moving on to clustering. So what we did is we take this, what we do is we take this VE matrix and then we subset it to only include the quote-unquote HPV genes. And what are the HPV genes? Those are the ones that have adjusted p-value less than 0.01 and log fold change, and a fold change of at least 2, okay? And so then if you do a dendrogram for that, so we pass that to hclust, and we do, the distance matrix we're going to use is this Pearson correlation. So we're kind of clustering based on a correlation metric, okay? And then if you plot the dendrogram, you get this gobbledygook, which is totally unuseful. And that's because you've got too many things being plotted down here, and you can't resolve all that. Now, there's ways to improve this. I could color code. What would be better, which I didn't do, is to actually, instead of applying the labels down here, color code all these points by either, for instance, red or blue to coincide then with HPV positive and HPV negative. And then you would know, all right, based on the clustering, where the HPV positive and negative are falling over here. And so that's a much more useful dendrogram. I didn't do it. Okay, but what I did do is I said, okay, well, let's cut it at level 2. If you cut it at level 2, it's cutting right here. And so we have 2 groups, which is all this group and all this group over here. All right? And then I calculated a tabulation of, here are the 2 clusters, 1 and 2, cross-tabulated with HPV positive and negative. And you see that cluster 2 is pretty much pure for HPV positive folks. And remember, now we're using genes that were found to be differentially expressed between HPV positive and negative, so we should see some separation of HPV positive and negative samples according to those clusters. But we don't see a complete separation because over here in the first cluster, we still have, while it has all the negatives, it also has some fraction of the positives, in this case, roughly 40%. And we'll see a little diagram that illustrates this here. All right, so here, right here is this code. I try to do a more stringent threshold and only use, in this case, there was 375 genes. I had a fold change of 4 and a p-value of 10 to the minus 8. So these things are really different, okay? Got it down to 375 genes. I redid the clustering, didn't make a hill of beans of difference, okay? So we still got some that showed up. We still have the same, roughly the same clusters. And this cluster contained mostly all HPV positive, and the other cluster contained all the HPV negatives, but then some of the positives too, okay? And then you can see why if we go down here, and now we're gonna redo this multidimensional scaling plot, all right? So we did this with all of the genes, but now we're gonna redo this multidimensional scaling with only the HPV genes, okay? And so we're only using the HPV genes, which were p-value less than 0.01 and fold change bigger of at least 2, to calculate the distance between the samples and then clustering in this space, or plot, assuming not clustering, but plotting the points. Each point, again, is a sample in this space. And you can see, we do have a pretty good separation over here of this group of HPV positives. They look to be pretty different, right, from these groups over here. So we could kind of separate out these folks. But there's a whole other group of HPV positives that are just intermingled with HPV negatives. And so we can't really tease those guys out, or those folks. So biologically, what it tells me is that there's some aspect of HPV status that you can kind of characterize with gene expression. And so for certain of those samples, that's true. but for other ones, it's not. So something else is going on, and I don't know what. All right, now, oh, this was totally whitewashed. It looks a little bit better on my computer screen versus up here. But I did it, everyone has seen a heat map, so we decided to do a heat map of these guys. And then it's the same thing. We're just going to use the HPV genes, right, and cluster. And this is two-way clustering, where you cluster using a dendrogram. This is clustering all the samples. This is clustering all the genes. And you can see the same thing here. We have this one little part of the dendrogram over here from hierarchical clustering, where it's primarily the blue is the HPV positive, the red's HPV negative, even though I don't have a key over here to say that. But mostly over here is HPV positive, and then most of over here is HPV negative, but there's some bleeding, so to speak, intermingling over here on this side. Okay. And I tried it also with k-means clustering just to try it out. And here's the result here. So k-means clustering, if we cut it at 2, had a more even distribution of numbers in the two clusters. Remember that hierarchical clustering had one small cluster and one very large cluster. And k-means clustering had a more even number of items in each cluster. And anecdotally, this is what I see in terms of when the difference between the two. I often do see this. When you do hierarchical clustering, I do see that the group sizes from hierarchical clustering can be very disparate and different, but in k-means clustering, they're similar in size. Again, that's just anecdotally, so I don't know if that's a universal truth, but it does seem to be the case every time I've done it. Okay. And then classification. So this is a survival analysis. So, to do all this, the starting point should be here is that you got to go to what Liambo did, copy and paste his code, and then modify it, right? Because to write all this de novo will take some time. But what we got is we got X is the expression data, and S is the survival data. And I'm not going to go through all the details, but we set a seed here, and then we randomly sample 2/3 of the subjects to be our training data, and then the subjects that are not included in this sample then become our test subjects. And so here's how and there's a function called sample, which will sample indices. So it's just if you want to sample 1 through 10, and you can tell it whether to do it with replacement or not. So I'm sampling 1 through the number of rows and sample data. How many items do I want to sample is 2/3 of that total. And then replace equals false means that each item is only sampled once. In other words, a subject is not going to show up more than once, right? If you put replace equals true, that means a subject can show up more than once in the same sample, okay? But we don't want to do that because we want a unique and split between the training and the test set. So these are the training subject, training IDs. And then to split up the matrices, I created this X-train and S-train and X-test and S-test. Whereas, if you remember this is going to give me all the subjects sampled in training index. This is going to give me, the minus here means that give me everyone except those folks, right? So that's the way to do it to make sure that those are distinct sets. And we fit the univariate Cox models. That code is the same as what Liambo did, so I'm not going to go over that. You can see then the distribution of p-values, and we have this spike over here, which means that, hey, there are some things associated with survival, okay? That means there is if nothing was associated with survival, what you would see is a flat distribution, a uniform distribution. But when you have this spike over here at the low end of p-values, it means that you've got an enrichment of things associated with it, and so you do have some things that are associated with survival. And then we can screen those top 25, and then here I picked the one that was the most associated. I don't know what this gene is, but maybe one of you do. So I looked and see, hey, just make sure, did I do this right? I went ahead and plotted Kaplan-Meier plots of this gene based on above and below their median expression. There was a difference. You see there, hazard ratio is about 0.5, okay? And if we keep on going, in the test data set, if I look at the test data set, you still see a difference, but it's not as big of a difference. P-value is not as significant. Hazard ratio is not quite 0.5. Okay? All right. So now last part I'll do is, it's 4:30, so we should finish up. So I did the 3 models, the backward selection with the AIC based on the 25, and I'm going to skip over all that part. Here is Kaplan-Meier curves for the test. This is the end result, which we split based on a median high and low risk for that model. And what do we get? C-index of 0.57, p-value of 0.04. This is in the test data. Okay, so keep that in mind. Then we do all this. I don't have time to go through all this stuff, but this is the lasso. And here's the end result we get from the lasso in the test data. And at least in my case, I didn't see, it didn't work, okay? Lasso didn't find me a very great model. Basically no difference, okay? But of course, I only did this once. To really know whether lasso works or not, you had to do it a bunch of times. Okay, and then still, even though it didn't really work, you see that there's still 11 genes in common between the 2 methods. So it still found some of the same genes. So it's a little surprising that it really failed. But I guess it found the wrong 11 genes. I don't know. Because I think there are only 14 genes in the other model. Anyways, so assuming I didn't make a mistake here, then for whatever reason it did not work. But using lasso, that starts with the top 25 univariate genes, and we're going to skip all that part with the lasso. And we get to this, and this is a little bit better than the stepwise selection. There's a little bit bigger separation. This is on the test data set. C-index is a little higher, closer to 0.6. P-value a little bit more significant. So anyway, so that's the end of it. And of course, like I said, if you wanted to really compare these methods and this, you might have to do more than just one split into a training and test set, do a whole bunch of splits and kind of see which one wins out. All right? And even after you do that, you still have to try and go find some external data set to validate whatever you did. All right, that's if you're holding the high bar. So that's it. So thank you all for sticking through to the very end of the workshop. I'm happy to entertain follow-up questions either now or after the workshop is done. And hopefully you guys can incorporate some of this into your own work. Or at least you have a better appreciation of what goes on. And if you do want to hire one of us to do some stuff, then you know where to find us. All right, you're welcome. Thank you.